Computer Science and Engineering Colloquia features accessible talks by leading computer scientists and computer engineers from across the region and around the world.
Welcome, everyone. It's my great pleasure to introduce today's speaker, Roger Grosse. He got his PhD at MIT. He's currently doing a postdoc at the University of Toronto. He has done an amazing breadth and depth of research in machine learning. He's won best papers at ICML and UAI, et cetera, et cetera. He's going to talk to us today about one of his research directions, which is exploiting compositionality to explore large spaces of models.
Okay, I want to begin by asking, how has the life of a machine learning engineer changed in the past decade? And I would argue one of the biggest changes is that a lot of tasks, which used to require a lot of human expert time, are beginning to be automated. Feature engineering used to be a big task if you were developing a system for computer vision or for speech understanding. But now in a lot of cases, we can train a neural network directly from the raw inputs, which can do as well or better than human engineered features. For algorithm configuration, there are software packages which can automatically tune metaparameters of machine learning algorithms, which are necessary for achieving good performance. In the domain of probabilistic inference, it can be a lot of work to implement a Markov chain Monte Carlo sampler or a variational inference algorithm. But there are software packages which, in certain cases, you can specify a model, and it'll automatically figure out how to do inference in that model. But when it comes to model selection, choosing models that we want to fit to the data, we still do this in a fairly ad hoc way. We might have some guesses of models that we think capture the right structure, and we try a few of them and see if they seem to work well. But we don't really have a reliable automated way of doing this. And so can we identify good models automatically? So there's some challenges involved. So if you think about the pipeline of probabilistic modeling, we'd first design a model, then we'd write an algorithm to fit the model, and then we'd somehow evaluate the model, maybe using a quantitative criterion or looking at what it's learned and seeing if it makes sense. And if we don't like the results, then it becomes an iterative pipeline. We'd go back and refine the model. And so if we want to automate model selection, then one of the challenges is that we'd need to automate each stage of this pipeline. We'd need to automate the design of the model, fitting the model, and evaluating the model. And the other challenge is that the space of models that we consider as machine learning researchers is huge. And so how can we narrow the space down into something more manageable that we can explore algorithmically? So in the first part of this talk, I'll give a proof of concept for the automation of search over model structures. And I'll focus in particular on the space of matrix decomposition models. In the second part of the talk, I'll go back and revisit some particular topics from the first part of the talk, which we can expand on and make more precise or more broadly applicable. So I'll first look at the first stage of the pipeline, designing a model. And I'm focusing in particular on matrix decompositions. What is a matrix decomposition? So here's the data set that we might be interested in analyzing. It consists of voting records from the United States Senate in the years 2009 to 2010. And it's represented as a matrix where rows correspond to senators and columns correspond to votes. And so if we look at a single row of the matrix, that tells us all of a single senator's votes. And if we look at a column, then that tells us the entire record of votes on a single motion or bill. And so how can we analyze this data set? One way to analyze it would be to cluster the rows of the matrix, cluster the senators. And we can do this using an algorithm like k-means. If we view this as a matrix decomposition, that corresponds to taking the matrix of observations and factorizing it as a product of a binary matrix, which represents the cluster assignments, and a real-valued matrix representing the cluster centers. And then we add to that another real-valued matrix that captures within cluster variability, or often we refer to it as noise. And so we can read off certain things from this representation. If we look at the rows of the first factor, we can read off which cluster a particular senator belongs to. Or we can read off which groups of senators tend to vote for a particular bill or motion. And so if we take the original matrix and sort the rows according to the learned clusters, then that reveals a certain structure in the original data. But alternatively, rather than clustering the rows, we might cluster the columns, cluster the votes. And this results in a different decomposition. It's a product of a real-valued matrix for the cluster centers times a binary matrix for the cluster assignments. And we can read off different things from this representation. We can read off what sorts of bills or motions one individual senator tends to vote for. We can read off which cluster a particular bill or motion belongs to. And if we sort according to this representation, we see a different structure in the data. But we're not limited to just clustering. We could also fit a low-dimensional approximation to the data using an algorithm like PCA. And this would correspond to factorizing the matrix as a product of two real-valued matrices. And from this representation, we can read off representations of senators or votes as vectors of real numbers. If we sort according to the dominant component in this representation, this yields still different insight into the original data. We can also go a step further, and rather than just clustering the senators or clustering the votes, we can cluster both. And this is a model known as co-clustering. And one way to think about this would be to start with the flat clustering model, where we cluster the votes, but then we recursively decompose the matrix of cluster centers using the clustering model, where we cluster the rows. And so this is a model where we simultaneously cluster the rows and the columns. And if we sort according to that representation, it reveals a block structure in the original data. And so we've just looked at a variety of different matrix decomposition models. And there are very many models we could possibly choose from. And so do these have anything to do with each other? Is there some way that we can automatically explore the space? And so I'm still focusing on the design of models, but now I'll describe a particular space of matrix decomposition structures, a space whose structure we can exploit algorithmically, both for fitting the models and also for organizing the search over the space of models. And so one observation is that we tend to build probabilistic models compositionally. We tend to combine different simple components in interesting ways. And this includes things like clustering and dimensionality reduction, which I've already talked about. But sometimes we assume that certain variables have heavy-tailed distributions. Sometimes we assume that functions are smooth. And there are a fairly large number of probabilistic modeling motifs that we combine in interesting ways to build models. And this is understood as early as the 90s, at least. It's been observed that we can organize different models from the machine learning literature into a lattice, where we can start with a structuralist model where everything is Gaussian. And then we can obtain different models by applying different motifs of probabilistic modeling. And so each edge in this graph corresponds to a particular motif. And so this is conceptually very nice, but it had a fairly limited impact on the algorithms we used, because every time you moved to a new node in this lattice, you need to start over from scratch, implementing an inference algorithm for fitting that model. And so I'll be talking about generative models. That's a particular approach to modeling that we take in machine learning. And I'll talk about I'll refer to the observations. That's the matrix that we actually observe, as well as latent variables, the things that we don't get to observe and that we need to infer. When we define a generative model, we define it in terms of a generative process, a story of how data sets get generated. And mathematically, what this gives us is a factorization of the joint probability distribution over the hidden variables and the visible variables. The factorization as a product of a distribution over the latent variables h times the probability of the observations given the latent variables. But when we're fitting generative models, what we're interested in doing is posterior inference. And so we'd like to take a data set and infer a particular explanation of how that data set was generated. And so in particular, mathematically, we'd like to find likely values of the latent variables in the posterior distribution, the probability of the latent variables given the observations. And so first, I'll talk about defining the generative process. So I'll define a space of matrix decomposition models that are constructed out of a small number of building blocks. These building blocks are all distributions over matrices. The first building block is the Gaussian distribution, which I'll represent with the letter G. And this corresponds to a matrix where all of the entries are independent Gaussian random variables. And this is useful for parts of the model where we don't want to assume any particular structure. The second component we can use is a multinomial distribution, which I'll represent with the letter M. And so this is a distribution over binary matrices that have a single one per row, and the rest are zeros. And these are useful for representing mixture models, like the clustering models I showed earlier. The third building block is the Bernoulli distribution, which I'll represent with the letter B. And this is a distribution over matrices where all of the entries are independent Bernoulli random variables. And this is useful for models where things can belong to multiple categories. And so a senator might be both an environmentalist, but also a fiscal conservative. And the last building block is a deterministic matrix. It's an integration matrix, which has ones below the diagonal and zeros above it. And I won't go into the details, but this building block is useful for models that have some sort of temporal structure, if the rows and columns of your observation matrix correspond to time. So those are the building blocks, and we can build models out of these as algebraic expressions. And so here we have a co-clustering model. Remember, co-clustering is where you cluster both the rows and the columns. And this is represented as the algebraic expression, mg plus g, whole quantity times m transpose plus g. And the algebraic expression gives us a generative process for the data. And that generative process corresponds to first taking all of the leaf matrices in this expression and sampling them independently from their corresponding priors. And then we evaluate the resulting expression. And so this defines a joint distribution over the latent variables and the observations. But we don't want to examine every possible algebraic expression because there's such a large number of them to choose from. And so I'll narrow down the space by way of a context-free grammar. And so this grammar will define the space of models under consideration. The starting symbol of the grammar is the completely structureless model represented by the letter G. This assumes that all of the data are independent Gaussian random variables. We can add structure by applying various production rules. So in particular, anywhere in our expression that we have a G matrix, we can replace that with a clustering model, mg plus g, where we cluster the rows. Or we can replace it with a clustering model, gm transpose plus g, where we cluster the columns. Or we could replace G with a low rank factorization, GG plus G. This would correspond to a dimensionality reduction model. But there are other motifs we can use. We can fit a binary feature model where things can belong to multiple categories. We can use models that assume some sort of temporal dynamics where things evolve as independent Markov chains. Or we can, rather than assuming a Gaussian distribution, assume all the entries are independently drawn from a heavy-tailed distribution. And we have a way of constructing heavy-tailed distributions out of the building blocks that I've already given you. But these production rules aren't standalone models. What's interesting is that we can build complex models by applying multiple production rules in succession. And so, for instance, if we want to get a co-clustering model, we can do that by starting with a structuralist model, applying a clustering production rule for the columns, and then taking the matrix of cluster centers and applying a clustering production rule to that. And so this gives us co-clustering. And there are a variety of examples from the machine learning literature which we can capture in this framework. And we don't necessarily get the original distribution exactly, but we can capture the same structure that they're interested in modeling with these models. And so how to interpret this figure is that we start with the completely structureless model at the bottom, and each of these arrows corresponds to applying a single production rule in the grammar. And so this is very similar to the lattice I showed you earlier in the talk. The difference is that it has a precise semantics. Each arrow corresponds to applying a single production rule. And because it has this precise semantics, we can exploit that both for fitting the models efficiently and also for organizing the search over the space of structures. So that was the space of models. How do we actually fit these models? And so here, we're interested in posterior inference, going from the observations to inferring likely explanations in terms of the latent variables. The strategy I adopt for fitting the models is a recursive initialization procedure. So in particular, if we've already fit a clustering model and we're applying the production rule for clustering to the matrix of cluster centers, what we do is we just fit a clustering model to that matrix. And so in particular, for each production rule in the grammar, each production rule corresponds to a simple probabilistic model. For each production rule, we write a special purpose inference procedure for that production rule. And so the upshot is that rather than implementing a separate inference algorithm for all the different models in the space, we just implement a single algorithm per production rule. We can also share computation between different models, because if we've already fit a clustering model and we're considering different successors to it, then we can make use of the work we've already done in fitting this model in order to fit the other ones more quickly. And finally, during this recursive initialization procedure, we can infer the dimension of the latent space using techniques from Bayesian nonparametrics. And so this is an initialization procedure, which we then follow up with a generic Gibbs sampler over the entire space. But because that has a hard time moving around, most of the work is actually being done by the initialization procedure. And so if we sit down to write special purpose algorithms for inference in a lot of these models, the tricks we might come up with would be things like eliminating variables analytically in order to simplify the problem and to help things move around the space more quickly. We might apply various linear algebra identities in order to avoid computing inverses of large matrices. We might identify tractable substructures in the problem, which can be solved exactly. Or finally, we can define high-level transition operators, which would perhaps split and merge different clusters. And so these are all tricks that we might come up with when implementing algorithms for specific models. But because our space is defined compositionally in terms of production rules, we can actually apply these in a flexible way across a wide variety of different models. So that was model fitting. If we're interested in model selection, we also need a criterion for evaluating the models. And I won't go into this in much detail right now. I'll return to it later in the talk. But the way we evaluate a single matrix decomposition model is to hold out a subset of the observations and evaluate the model based on the probability assigned to those the held out data conditioned on the observations. So finally, we want to close the loop. If we've already evaluated a model and we don't like it, we'd like to be able to take what we've learned and go back and refine the model and come up with something better. And so in particular, we want to do an automatic search over the space of matrix decomposition structures. The key challenge is the space is very large. In fact, there are over 1,000 different models that are reachable within only 3 production rules. And so we don't want to do a brute force search over the space. So how can we narrow down this large space in order to obtain a small set of promising candidates to evaluate? I'll take inspiration from the history of research on models of natural images. So back in the 80s, people noticed that if you take a patch from a natural image, let's say 12 by 12, you could model it in terms of combinations of uncorrelated basis functions. And this results in a Fourier representation. In the 90s, people noticed that the coefficients in this representation have a sparse distribution. And so if they encode the sparsity in the model and fit that, then they wind up with a set of oriented filters similar to the representations you find in the primary visual cortex, in particular the simple cells in the primary visual cortex. In the 2000s, people went a step further and modeled the dependencies between the magnitudes of different variables. Or in particular, you can think of it in terms of the dependencies in the sparsity pattern in this representation. And what they wound up with is a high-level textual representation. And they actually found that the representation was similar to that of complex cells in the primary visual cortex, one level above simple cells. And so the unifying pattern here is that they would start with a model that's already been fit. They look at the learned representation, and they see if there are interesting dependencies that aren't already captured by the model. And if they find anything, then they add that to the model and fit that. And so in the context of the matrix decompositions grammar, refining a model corresponds to applying a production rule. And so we use a greedy search procedure inspired by how we often build models. So in particular, we start with the completely structuralist model. And in each stage, we take the best model we have so far. We apply all possible production rules to it. We fit and evaluate those models. We pick the best one of those, and we repeat. And so it's a greedy search procedure, and perhaps it sounds fairly simplistic. And we don't know ahead of time whether this procedure is likely to work well or not. It's really an empirical question. And how do we measure it empirically? One way would be to run this system on simulated data where we know the correct structure. And so here we have a table where each of the rows corresponds to a particular matrix decomposition model. And the columns correspond to different levels of noise, which increase as we move to the right. Each entry of the table corresponds to the structure that this automated model selection procedure came up with. And in each of these cases, it could have chosen anything. There's a huge space of models that it could possibly come up with. But we see that under low noise conditions, it's generally able to identify the correct model structure. The numbers here tell us how many steps it would have had to do differently in order to arrive at the correct structure. If we crank up the noise, interestingly, it falls back to simpler and simpler models. In fact, it just predicts a completely structuralist model a lot of the time if it's not able to pick up the signal in the data. We can also run the system on some real-world data sets and look at the representations that it learns. So if we run it on the data set of Senate voting records that I've used as the running example, the first thing it does is to cluster the votes. And it comes up with 22 clusters. There are some big clusters for things like party line Democrat, party line Republican, uncontroversial things that everyone votes for, but then also some smaller clusters for individual issues, things like veterans' health, immigration, and so on. In the second step, it clusters the senators. It finds 11 clusters and no cross-party clusters. And in the final step, it doesn't find anything that improves significantly on the model in the second step. So we set a particular stopping criterion for the amount of improvement that's expected relative to the previous model, and it decided to stop after the second step. We looked at a data set of human motion capture data. This is data of a person walking in various styles. And it's a matrix where each row corresponds to a particular time step. And it gives the person's displacement as well as various joint angles. The first model our system comes up with is to model all of the joints as independent Markov chains. So everything just evolves independently in time. And then in the second step, it picks up the correlations between the movements of different joint angles. We looked at a data set of patches drawn from natural images. And so this is a matrix where each row corresponds to a 12 by 12 natural image patch, which has been flattened into a vector. And so when we run our system on this data, it starts by fitting a low rank approximation similar to principal component analysis. Then in the second step, it sparsifies the coefficients in this representation to get the sparse coding model. In the third step, it picks up the dependencies between the scale variables in this representation, yielding a model similar to that of Karkelin and Lewicki from 2005. And so it's quite striking that this completely automated procedure explores the same sequence of models that the natural image statistics community has explored.
What's the motivation for blurring and whitening the images, or blurring in particular?
So that's just a standard pre-processing step that that natural image statistics researchers have used for this data. I think the blurring is to avoid certain corner artifacts. I think it turns out if you fit a sparse coding model without doing that, then you get a bias towards horizontal and vertical edges. And so that's kind of a standard pre-processing step. And finally, we looked at a data set that's been used to analyze human concepts. This is a matrix where each of the rows corresponds to a particular kind of entity in the world, like house or pineapple. And each of the columns corresponds to a question that people were asked about this, like, can it fit in your hand? In the first step, what our system does is it clusters the entities. In particular, it finds 39 different clusters, and they tend to be fairly interpretable things, like buildings, tools, foods, and so on. In the second step, it finds a low-rank representation of the cluster centers. And it finds an 8-dimensional space, but the two largest dimensions correspond, first of all, to living versus non-living, and then second, to large versus small. And so that was the first part of the talk. I gave a proof of concept for automatically searching over matrix decomposition structures. In the second part of the talk, I want to go back and revisit particular parts of this pipeline and see if we can do it in a way that's either more broadly applicable or more scalable. So first I want to go back and revisit the design of models. I talked about a space of matrix decomposition structures. Can we apply these techniques to a different space of models? And so in particular, I'll look at compositional structure search for Gaussian process models of time series data. And this part of the talk is primarily the work of my collaborators, Dave Duveneau and James Lloyd. So Gaussian processes are distributions over functions. And the distributions are specified in terms of kernels. And I won't go into the mathematical details, but there are various primitive kernels that we can choose from. There are kernels that give us distributions over smooth functions, distributions over periodic functions, distributions over linear functions, and so on. But what makes this space interesting is that we can take different kernels and we can compose them by adding or multiplying them. And so in particular, if we take two linear kernels, we get a distribution over quadratic functions. If we take a linear kernel plus a periodic kernel, then we can get a periodic function with a trend. Or if we take a smoothness kernel and multiply it by a periodic kernel, we get a distribution over functions which are locally periodic, but the structure changes over time. And there are a lot of interesting ways that we can combine kernels together. And just like I discussed algebraic expressions to represent matrix decomposition models, we can represent a lot of interesting Gaussian process models as algebraic expressions, combining different kernels. And just like our greedy structure search over matrix decompositions, we can also do the same kind of structure search over Gaussian process models. So we can start by assuming no structure, assuming everything is just white noise, and then we can explore different kernels that apply to the data and evaluate them. And so if we choose this particular kernel, then we can look at different ways to extend that. And so we do a greedy search over the space of kernels. What this yields in the end is, for a particular time series data set, we get a highly structured kernel that captures that data. And so this consists of sums and products of 4 different primitive kernels. And once we have this representation, we can decompose the time series into interpretable components. In this case, this is the data set of radio critical frequency. This is the highest frequency that can be broadcast at any particular point in time. It depends on atmospheric conditions, solar activity, and things like that. And this data set turns out to decompose into a smooth function plus a periodic function plus a periodic function that changes in amplitude plus some noise. And we don't just get the decomposition, but we can also extrapolate beyond the range of the observed data. And so if you use a structureless kernel that just gives smooth functions, then the extrapolations tend to be very poor. But if we use a highly structured kernel, then it actually extrapolates beyond the range of the observed data in fairly sensible ways. The second topic I want to revisit is model fitting. So I talked about fitting models by performing posterior inference. But if we're trying to fit large models to large data sets, then we might instead use optimization rather than inference. And so I talked about using the structure of a space of models in order to perform probabilistic inference. Can we use the structure in order to optimize better? And so I first want to point out that if we're training a neural network, we can look at training curves, but that's often very deceptive. So in particular, the optimization objective might appear to level off over time. And so we look at this and we think, OK, it's almost done training. Might as well stop here. But then actually, if you run 10 times longer, you see that it is actually still improving. It's just improving very slowly. So why do we get this slowdown? Well, most neural networks are still trained using stochastic gradient descent. And that's a training procedure where in each iteration, we pick a training example or a handful of training examples, and we update the parameters in the direction that decreases the cost function on those training examples. And it's intuitively nice, but it has problems when the loss function is badly conditioned. So for instance, if we have a very elongated loss function, what happens is that the algorithm bounces around really quickly in directions of high curvature, and it makes very slow progress in directions of low curvature. Natural gradient descent is an algorithm that's been proposed to remedy this situation. So it's an algorithm that comes from the field of information geometry. It was proposed by Shinichi Imari in '98. And the motivation is gradient descent can be thought of as steepest descent in the Euclidean distance metric over parameters. And so the direction that decreases the first order approximation to the loss function. Natural gradient descent is steepest descent in a distance metric that reflects the curvature of the loss function. So that would correspond to this quadratic. And so the natural gradient is the direction which decreases the loss function the fastest relative to this more meaningful distance metric. And so the upshot of natural gradient descent is that it can take large steps in directions of low curvature without things becoming unstable in the high curvature directions. And so if we could actually compute the natural gradient, then that would be fantastic. Unfortunately, the formula for the natural gradient consists of the inverse of the Fisher matrix. And I'll tell you later what the Fisher matrix is. But it's the inverse of the Fisher matrix times the log likelihood gradient. And the dimension of the Fisher matrix is the number of trainable parameters in the model. And modern neural nets can often have tens of millions of trainable parameters. And so we can't explicitly represent a 10 million by 10 million matrix, let alone tractably invert it. And so what can we do? The approach I've taken is to treat this as a probabilistic modeling problem. So in particular, the Fisher matrix F, it's the covariance matrix of the log likelihood gradients. And so conceptually what that means is that if we sample the log likelihood gradients around our current location, these gradients will tend to be large in the directions of high curvature and small in directions of low curvature. Then the Fisher matrix will be the covariance of those samples. But we don't want to fit a full covariance matrix because that would be too large to represent. And so instead, we want to find a tractable model to the distribution over log likelihood gradients, but one which still preserves the important structure in the distribution. And this is an unusual probabilistic modeling problem because normally we try to build models of data. In this case, we're trying to build a probabilistic model of the computation of the log likelihood derivatives. So we're trying to model computation. And the details are beyond the scope of a broad audience talk, but in general, the strategy that I've taken is to impose conditional independence structure based on both the structure of the computation graph, the graph saying how the derivatives are computed, but also empirical observations about the distribution over the log likelihood derivatives. And this work combines ideas from differential geometry, optimization, and probabilistic graphical models. I've talked about various sorts of matrix factorizations, but the upshot of this modeling is that it results in factorizations of the Fisher matrix, which can be represented in linear size as a function of the original model size. And we also can compute natural gradient updates in linear time, given this model. And so in the end, each of the updates for this approximate natural gradient algorithm, each of the updates is comparable in computation cost to stochastic gradient descent, but it's much more effective in terms of decreasing the loss function. Right, we want the inverse of the approximation to f. And as it turns out, the probabilistic model I fit is one such that the inverse can be tractably computed. And I'm happy to talk more about it offline. And so how well does this work? So we evaluated it on training restricted Boltzmann machines. That's a kind of generative model that we use as a building block in the field of deep learning. And we looked at two distribution modeling benchmarks, a data set of 100 digits and a data set of 100 characters in a variety of world languages. And compared with stochastic gradient descent, which is how these models are normally trained, we can obtain quite significant speedups. In these cases, 22-fold and 5-fold. We also looked at optimizing convolutional networks, an architecture which has become very widespread in the field of computer vision. And we looked at two object recognition benchmarks, CFAR10 and the Street View housing numbers. And we can obtain quite significant speedups in training convolutional networks, both in terms of the training accuracy and also in terms of test accuracy. So depending how you measure, anywhere between a factor of 2 or a factor of 7. And this is a kind of model where it's been very difficult to improve at all over stochastic gradient descent. A lot of people have invested a lot of effort in doing this. And interestingly, the speedups appear to get even larger if we're in a highly data parallel setting. So if you're trying to train a network on a large cluster, then you need to, and you want to distribute the data across different machines, then it appears there'll be even more advantage to taking account of curvature information. The final topic I want to revisit is model fitting. We often evaluate probabilistic models based on probabilistic criteria. What's the probability of the observations with all of the latent variables integrated out? Or if we hold out some unseen test examples, what's the probability the model assigns to those test examples? And we have algorithms for approximating this, but we don't really know how well they work. And so how can we come up with likelihood estimates that we can actually be confident about? First, I want to point out that if we're trying to evaluate generative models, there's a seemingly appealing criterion you might use, which is the generative model represents a distribution over the inputs. So why not just take the distribution and draw samples from it and see if they look good? Well, if we look at these two sets of samples from model A and model B, who thinks model A is a better model of handwritten digits? Who thinks model B is a better model? So actually, model B is a model that is actually fit to the data. Model A consists of taking a random example from the training set. And so it gives great-looking samples, but it's unlikely to generalize, and it's unlikely to give us much insight into the data. And so we need a quantitative criterion for evaluating generative models. And so as I mentioned, one criterion would be to hold out a subset of the data and measure the probabilities assigned to that held out subset. And it's great statistically. There are a lot of reasons this would be a good thing to do. But unfortunately, it's intractable for a lot of models. And so in particular, models like Markov random fields, Boltzmann machines, and Markov logic are defined in terms of an unnormalized distribution. And they also have a normalizing constant out in front. That normalizing constant is the partition function. And it's something which is generally intractable to compute. And if we can't compute the normalizing constant, we can't compute the probabilities. Probably the state-of-the-art technique for estimating log likelihoods of Boltzmann machines is an algorithm called annealed importance sampling. And it's believed to work well, but it has the drawback that it gives a stochastic lower bound on the log partition function. And unfortunately, the log partition function is in the denominator. So if we underestimate the partition function, we overestimate the likelihood. And so we could be vastly overconfident about how good our model is. We don't know if we have a great model or a terrible partition function estimator. And it's not just true about the particular AIS algorithm. Other algorithms tend to overestimate the log probability of the observations. And here's an example of trying to evaluate a restricted Boltzmann machine. If we run annealed importance sampling in the usual way, so here we have the number of steps taken on the x-axis on a log scale. And so it appears to be leveling off. Maybe we're not quite sure. But if we run the algorithm using a different parameter setting, then it appears to level off to something different. And because these are both stochastic upper bounds in the true value, we know that the first one was wrong by at least 18 nats. And so we know that the model is at least 8 to the 18 times worse than we thought initially. But we're not done yet, because the true log likelihood could still be much lower. It could be anywhere between here and minus infinity. And so the approach that we take is to define an approximate generative model such that it's parameterized by a computation parameter. And as that computation parameter goes to infinity, it approaches the distribution of the original model. But the approximate model is one such that we can actually obtain good stochastic lower bounds on the log likelihood. And this is an estimator that we call the reverse AIS estimator. Applied to this problem, that gives us the blue curve. And so that the two bounds actually meet. And we're not guaranteed that these are bounds on the same thing, so we don't have rigorous guarantees about the true value. But heuristically, we can be a lot more confident that we're actually estimating the likelihoods well. And it doesn't work just for restricted Boltzmann machines, but it also works for other models defined in terms of Boltzmann distributions, such as deep belief networks and deep Boltzmann machines. So that was the domain of estimating held-out likelihoods. But also, we sometimes want to estimate marginal likelihoods. So what this means in the case of matrix decompositions is that we want to compute the probability of the observed data with everything else integrated out. We want to sum or integrate out all of these matrices and all the parameters associated with those matrices. And so it's a huge, high-dimensional summation and integration problem. And computing the marginal likelihood is intractable for a lot of models that we care about. And what's worse, we don't even know how good our algorithms are for estimating the marginal likelihood. So here's an example of trying to estimate marginal likelihoods for a particular matrix decomposition model. And what we see is we have 4 different algorithms, which are all believed to be pretty good. And we have the amount of computation on a log scale. And what we see is that they all appear to level off, but unfortunately, they're leveling off to different things. And so this is a bit troubling. It turns out that we have the reverse image of the situation from models with Boltzmann distributions. It's very easy to obtain stochastic lower bounds on the marginal likelihood, but unfortunately, we don't have upper bounds. And so the true value could still be anywhere between here and plus infinity. So our novel contribution is a technique for obtaining good stochastic upper bounds on data simulated from a model. So it doesn't work for arbitrary data sets, but it works for data that are simulated from a model. And what we actually get is this curve. It's a stochastic upper bound, and as we increase the amount of computation, it actually meets the lower bound. And so we can obtain the true value provably with high accuracy. You're not guaranteed that the bounds will converge in polynomial time, but if you're lucky enough that they do converge, then you have a provable estimate of the true value. And the upshot of this is that we can combine the upper and lower bounds to obtain ground truth marginal likelihood values for data simulated from a model. And we can use that ground truth value to evaluate a lot of different marginal likelihood estimators. And so here we have computation time on an x-axis on a log scale and mean squared error on a log scale. And we have a variety of different marginal likelihood estimators that have been proposed. And what we find is that there are actually orders of magnitude difference in the amount of error that different estimators achieve. And this is something that we weren't able to quantify before. We can also ask how much accuracy do we need? And so in particular, if you want to distinguish different matrix factorization models, like does the data come from a clustering model or a low rank approximation, this is about the level of accuracy that we need. And we find that there are really only a handful of algorithms that give us that level of accuracy. And unfortunately, we need to run them for a long time. But I think now that we're able to quantify the performance, we can start to do science and start to improve our marginal likelihood estimators. So to summarize now, I think there are two fundamental challenges whenever we're trying to automate a machine learning task. The first fundamental challenge is how we can take the specification of a model and use that to construct efficient algorithms, either for posterior inference or for optimization. And so I've talked about automatically constructing algorithms for probabilistic inference and structure search in the domains of matrix decompositions and Gaussian processes, and how to construct good optimizers based on the structure of a neural network model. The second fundamental problem is how can we tell if an algorithm is giving good results? If we want to hand over control to a black box, we at least want to be able to measure if it's doing the right thing. And so I've talked about this both for evaluating likelihoods of Boltzmann distributions, and also for evaluating the accuracy of Monte Carlo estimates of the marginal likelihood. And I'd like to thank a lot of wonderful collaborators without whom this wouldn't have been possible. And finally, if you're interested in learning some more background about some of the techniques I've talked about, I've been working on a website called MetaCademy, which takes a dependency graph of the core concepts in machine learning and related fields, and uses the dependency graph to provide personalized learning plans, step-by-step plans all the way from probability spaces and vectors to more advanced concepts like restricted Boltzmann machines. And for each concept, it has links to resources where you can go and learn about it. And so a lot of people, a lot of beginning grad students have found this very useful in getting acquainted with the field. So I'd like to build on this, first of all, by automatically trying to identify good neural network architectures. If you've been following the neural network literature from the past few years, it's gone well beyond questions of how many layers, how many units, and a lot of very interesting components have been proposed, things like visual attention, external memory controllers, and so on. But these components have a lot of internal structure, and it's fairly controversial which parts we actually need, why do we need them. And there's been some work on tensor representations, where instead of having weight matrices, we have weight tensors that capture higher order interactions between variables. But if we want to represent that compactly, we need to somehow factorize the tensor. And there are just an enormous number of different factorization models to choose from. And so how can we explore that space automatically? Following up on automatic model fitting, on the theoretical side, I'd like to understand if the procedure that I've been using for recursive initialization is actually justified. So if we're given oracles which can perform inference in simple models like clustering and dimensionality reduction, can we use these oracles to perform inference in more complex models? Or is there something fundamentally harder about these complex models? On the more practical side, automatic inference is a big part of what makes a system like that possible. But we don't just want a system that produces a single answer. We also want calibrated estimates of the reliability of that answer. Following up on the work on information geometric learning and approximations to natural gradient, I think there are a lot of fascinating theoretical questions in terms of how to make it more proper. So the approximations to natural gradient were defined in terms of coordinates, the very things we're trying to get rid of when we apply differential geometry. And so I'm interested in trying to build scalable machine learning algorithms directly out of differential geometric primitives so that we can automatically get a lot of the invariance properties that we care about when trying to train neural networks. On the practical side, there appear to be large gains of accounting for curvature in a parallel setting. And so can we build massively distributed learning systems which can exploit curvature information? And finally, I talked about modeling computation, in particular modeling computation of derivatives for purposes of optimization. But I'd like to go a step further and actually model the full learning process, partly so that we can gain some insight from analyzing all of our experiment logs. I'd like to be able to reverse engineer what a network is doing. So we're starting to be able to train neural networks that can solve problems like sorting lists without us understanding how they're solving them. And I think it would be great to be able to reverse engineer what algorithm they're using by fitting a model to what they're doing. And finally, I'd like to fit models that allow extrapolation. So figuring out how well an algorithm would perform if we give it 100 times more resources, more data, more computation. What will we be able to learn with the hardware of 10 years from now? And so I think all of this will combine to give systems that make life easier for machine learning researchers and augment the space of models that we're able to learn effectively. So I'll open it up to questions. Yeah.
What do you mean when in the last part where you were talking about the estimators and you were getting estimators in the other direction from synthetic data, and exactly what does it mean to have these different estimates approaching each other? How should one really interpret those?
Right. So in this figure, these estimates are all for a single data set that was simulated from a model. And so these are all upper or lower bounds on the same quantity. And the x-axis is the running time. The algorithms all have parameters which manage the trade-off between computation and error. And so when I say that the two bounds converge to each other, that just means that as we run the algorithm with more and more computation, that the bounds on that quantity get tighter and tighter.
I see, but these are for simulated data. Now, when you apply this in a situation when you have real-world data, what happens?
Right, great question. And so we don't really have bounds on what will happen with real-world data. And so it could tend to overestimate the performance just because the real-world data might somehow be harder than the simulated data. And so we don't really know. And so it's really a heuristic measure. And so how I would envision this being used in practice would be if you're trying to fit a model, you'd first generate some data from that model and figure out how long you need to run your algorithm in order to get good estimates. And then that tells you how long to run it for real data. But there are no guarantees. It's a heuristic.
To clarify, since you didn't explain the algorithm, why does it only work for simulated data?
Right. So the thing that we make use of is an exact sample from the posterior distribution. And so if you have a single exact sample, then it turns out that that helps us get certificates that something is a stochastic upper bound on the log likelihood. And so the exact sample is what we make use of. And the reason that simulated data helps is that if we simulate data from the model, then the parameters and latent variables that we use to generate the data also turn out to be an exact sample from the posterior. And so for simulated data, we have available to us a single exact sample. And that turns out to be enough to get certificates.
Yeah?
So how does the natural gradient learning differ from the Hessian tree optimization, which was like Martins and...
Mm-hmm. Yeah, and so I was actually collaborating with James Martins on this work. And so it's similar in spirit to Hessian free optimization. So there's sort of multiple parts to this question. So there's a question of Hessian versus Fisher matrix. So Newton's method is a second-order optimization method that uses the Hessian to approximate curvature, and natural gradient instead uses the Fisher matrix. And the Fisher matrix can be viewed as an approximation to the Hessian. But what makes it useful in the context of training neural nets is that even for a non-convex problem, the Fisher matrix is guaranteed to be positive semi-definite. And so you know that you wind up with a descent direction, whereas Newton's method might just look for a saddle point. And so that's Newton's method versus natural gradient. And this is partly inspired by James's work on Hessian-free optimization. But how it differs is that that work applies a iterative procedure to approximately solve large linear systems. And so each time you compute an update, you might need to do 30 times as much work as you would do for the stochastic gradient descent update. Whereas what we're doing here is we're fitting a model to the distribution over the log-Colloquia derivatives. And using that model, we can compute an update in one step. And so it actually only requires a small constant factor, more computation to compute than a stochastic gradient descent update.
Any other questions? All right, let's thank Roger once more.